All right, welcome to this explainer. Today, we are going on a truly mind-bending journey. Our ultimate goal? We're going to calculate pi. But we aren't going to do it the normal way. No, we're going to calculate pi perfectly from pure geometric scratch using a massive, highly complex system of formal logic known as Coq proofs. We're literally talking about building a mathematical universe from the ground up, moving from simple one-dimensional sequences all the way into the fourth dimension just to mathematically force the universe to hand us the exact undeniable value of pi. Okay, let's dive into this. So here's our roadmap. We're going to kick things off with the quest for pure pi, look at the golden ratio connection, lay down the Fano plane foundation, navigate the fourth dimension, jump into the Polybius diagonal race, and finally, converge on final truth. It's a lot, so let's get right to it. Part 1. The quest for pure pi. So here is the massive problem at the heart of this whole explainer. How do you actually find pi if you're not allowed to look it up? I mean, usually we just cheat, right? Just like human memory relies on instantly recalling 3.14, modern computers, even the massive data centers powering the internet, they all just rely on cached floating point approximations stored in their servers. It's an incredibly close guess, sure, but it's still just that, a guess. We don't want the data center's approximation. We want absolute, pure truth, derived entirely from geometry. And to guarantee that purity, just take a look at this exact constraint, pulled straight from the Coq source code we're analyzing today. No stored pi constant. That is literally a true-false proposition in the code, proving that we are building this entire mathematical universe with absolutely zero pre-programmed constants. We've got to earn every single digit of pi using nothing but shapes and pure logic. Now, to pull this off without cheating, the source code sets up what it calls a projection boundary. You can basically think of this as a super strict protocol firewall. On one side of the firewall, you've got perfectly exact finite geometric structures, points, lines, shapes that you can count precisely. But on the other side, that's where you find the messy, continuous world of real numbers, fractions, and square roots. We have to completely build our perfect machine on the geometric side before we ever cross that boundary to get our real number pi. Which brings us to section 2, the golden ratio connection. Before we can even get to pi, the code mechanically derives classical phi, which you probably know as the golden ratio. And the way the algorithm does this is just wild. It proves that phi is naturally derived from the 3D geometry of something called the rectified 3-5 common core. That's basically a structural relationship with 30 vertices, 20 triangular faces, and 12 pentagonal faces. So it's literally pure 3D geometry handing us our very first crucial constant. And to actually calculate it without cheating, this phi iter code takes us on a bit of a walk. We start with a ratio of 1. Then we apply a really simple iterative step, 1 plus 1 over x. And the code mathematically proves that this humble Fibonacci sequence mechanically marches us directly and infinitely toward the golden ratio. So we've conquered 1D sequences, we've conquered 3D shapes. Next, we need a 2D scaffold. All right, section 3, the Fano plane foundation. The source code introduces this incredible structure called T0 Fano incidence. This is the Fano plane. It's a beautiful, unbreakable, and finite two-dimensional geometric scaffold. And remember that firewall we talked about? Well, the Fano plane lives entirely on the exact, pure side of that boundary. There are absolutely no messy fractions here. Just look at these strict rules. It contains exactly 7 points, exactly 7 lines. Every single line has exactly 3 points, and every single point connects exactly 3 lines. Every pair of points has one and only one unique line connecting them. It is a completely closed, perfectly balanced equilibrium. And this exact 7-point geometry, it becomes the bedrock for the selector algorithms that will eventually pick the fractions we need for pi. Moving right along to section 4, navigating the fourth dimension. Okay, look at the mind-boggling balance relationships defined in these Coq proofs. We are suddenly looking at massive 4D shapes known as polytopes. We're talking the 5-cell, the 24-cell, and the absolutely massive 600-cell with its 1,200 faces. The source code meticulously maps out all of their vertices, edges, and faces to prove that their symmetries are fundamentally intertwined. The geometry of a 120-vertex 600 cell perfectly balances out against the structure of the smaller shapes. But how do they actually connect? Well, they connect through a mathematical centerline. The code introduces the Triachus tetrahedron, which is an 8-vertex shape. And the formal proofs specifically show that this shape acts as a perfect mathematical bridge, balancing all those crazy 4D symmetries. 8 vertices perfectly equals one 4-vertex tetraunit plus another 4-vertex tetraunit. It's wild. We've built an enormous, perfectly balanced, static structure out of dimensional shapes. But now we have to put it all in motion. Section 5. The Polybius diagonal race. So, to actually calculate pi, we need an infinite series of fractions. To get those, the code defines something called a chiral phase. These are essentially alternating mathematical states that bring all our pure static geometry to life. Specifically, the code calls them the D+ phase and the D- phase. You can kind of think of them as two engines built entirely out of the 4D geometry we just looked at, and they're taking turns driving us forward. And notice just how mathematically tight this race really is. The D+ phase has a sign of +1. The D- phase has a sign of -1. But look at their internal properties based on the code's logic. They both have an exact XOR logic closure of 0, and they both sum to exactly 30. So they are perfectly balanced, yet they push in completely opposite directions. Let's look at the mechanics of the race itself. The D+ and D- phases alternate continuously, and a system called the diagonal accumulator tracks every single one of these state changes. This back-and-forth race literally forces the generation of a perfect mathematical sequence. Then structures called BQF bridges, which use this formula of 16 times x times y, they link this geometric orbit to the actual denominators we need. So the geometric phases are battling it out, and the accumulator is catching the exact fractions required for our pi calculation, finally crossing over that firewall boundary we set up at the very beginning. Which brings us to the grand finale, Section 6, Converging on Final Truth. Before the code declares total victory, it runs a quick safety check. It takes this massive geometric scaffold, the Fano plane, the 4D polytopes, the diagonal accumulator, and it mathematically proves that the final output, which it calls OMI_pi, is strictly bounded between the numbers 3 and 4. The system is stable, the logic is totally unbreakable, and then we get the ultimate theorem. This is the exact line of code where the compiler says, yes, this is true. OMI pi from diagonal accumulator equals pi. The Coq proof mathematically guarantees that this highly complex, alternating 4D geometric accumulator perfectly outputs the exact continuous real number of pi. No cheating, no floating point approximations, just absolute, pure truth, derived entirely from shapes. Which really leaves us with something incredibly deep to think about. If we can build an entire digital machine out of purely abstract shapes, from a simple 7.2D plane to a massive 600-cell 4D polytope, and use them to run a literal race that mathematically spits out the exact infinite digits of pi, is the very fabric of our universe ultimately built on numbers, or is it built on geometry? I'll leave you to ponder that deep connection between dimensional geometry and pure computation. Thanks so much for joining me for this explainer, and keep exploring the shapes behind the math.